So good afternoon, everyone. Welcome to the Real-Time Analytics Track 2, a breakout session for Flink Forward Asia 2025. Let me introduce myself first. My name is Yuan Mei, and I am the Director of Engineering at Alibaba Cloud, as well as your host for this session. So I'm thrilled to guide you through our exciting lineup today, which highlights the cutting-edge developments in real-time analytics, streaming computation, and the incredible innovation happening within the Apache Flink ecosystem. This track will showcase talented experts from leading organizations sharing their insights and the practical implementation of Flink. Whether you are here as a developer, an engineer, or decision maker, I hope you will leave inspired with new ideas to take back to your teams. Now, to kick off things, it's my honor to not only introduce but also deliver the first session. So my talk title is Flink State Management, a journey from core primitives to next generation incremental computation. So let me start. Put this down. Oh, thanks. We go to the next stage. So in the past few years, we actually have did a lot of efforts in the Apache Flink community to make the architecture cloud native. And in today's talk, I'm going to share some of these achievements. And specifically, I'm going to talk about the Flink state management, specifically from core primitives to disaggregated state architecture, and to next generation incremental compute. So Flink is a high-performance, distributed in large-scale streaming processing engine, and it is standard for real-time processing. Nowadays, it's already being trailed in people's mind, but behind it, stateful computation is the driving force. So in the early stage, when I was still a student, the stream processing actually couldn't do too much more than a simple ETL. And if you want to do a little bit more complicated things, like to correlate the historical data, you're going to have to rely on external database. And that is not only make the deployment and also the maintenance difficult, it also cause the data correctness and the consistency issue. So then a game changer came in. That's Flink, with its self-maintained state management mechanism, which enables Flink the capability to memorize things. So it's very important that Flink now have the memory. With this memory, it actually could do much more complicated things. It does not rely on any external databases anymore. So this state management system was first introduced in 2017 in the VODB paper, and it laid the foundation for where Flink stands as it is today, as a standard of real-time processing. And this year, we make a step further. So we changed the architecture from the local embedded state to disaggregated computer state. And our achievements was written in the paper and accepted in VODB 2025. So this will happen in 2 months in September, and I will present there. And with this architecture improvement, it's actually solved a lot of problems about large states, and people complaining all the time, oh, I have my state large, and how can I make the state small and reduce the cost? And what's next? And we are hearing people or users complaining. And the next step in the future is to lower the real-time processing costs through the generic incremental compute. You see, the generic is much bigger than other words. I will explain why it's bigger in the following slides later. But our mission is to make real-time processing affordable by everyone. So that's basically the timeline of this talk, and I'm going to go through. And after this talk, I hopefully we could answer these questions. So what Flink state is capable of? what problems we encounter when we are using the state and how we solve them, and what's next, and how to reduce the cost. So let's start from what exactly is state in the context of stream processing. State is the memory of your streaming applications. It enables your application to remember past events, and based on those past events to influence the future processing. So for example, it could be accumulated sum, count, or for window aggregation. It could be existing feature parameters in the streaming join. It also could be transaction histories to do the fraud detection in CEP. And the state is fundamental to stream processing. And without stream processing, you see, without the state management, it could only do the simple ETL, right? So it enabled complex stateful computations and composite the state altogether. I will show you later how complex a query could be. And then it provides a mechanism and hide all the complexities to ensure system consistency and correctness. And also it underpins robust fault tolerance. So this is the complex stateful computation as a real-world use case in the Alibaba Cainiao real-time logistic use case. So you see, so this is the use case that's tracking the package, the order package, and through the supply chain. And based on these information updates, you could do the detection or the other analytics. So what exactly is it? So the order packages are coming from different e-commerce platforms. As you know, like Alibaba has different e-commerce platforms as Tmall, Taobao, AliExpress. And since those orders are coming from different sources, so they have to be union and deduplicated first. And then after the shipping event comes, it would be joined with the order updates and generate the updated logistics and order status. And those information would be used to help to do the logistic anomaly detection using CEP. Or based on this information, you can further calculate the metrics, for example, the on-time shipping rate by order, and then analyze whether those, which sources have had problems, and etc.
What is Taobao?
Ah?
What is Taobao?
Taobao. Taobao is is a e-commerce platform. People can shop there. Yeah. So here is a summary about the Flink state management, what it's capable of. I grade it into 4 categories. First, as we said, it is empower complicated stateful stream processing with aggregation, join window, pattern detection, real-time machine learning. The second is it guarantees exactly one's semantics by providing a global checkpointing and atomic recovery. And in this way, it can guarantee data consistency. And then the third part is it enables event time and out-of-order handling, which is very important in stream processing because your data is coming out of order. And so it provides accurate time-based results and graceful late data handling and guarantee data correctness. And lastly, it enables scalability and elasticity for Flink because it partitions and distributes state across different nodes and organizes the state as disjoint key groups, and which can enable dynamic scaling. Okay, so here is the first generation of state management. And at the very early stage, state is stored as a JVM heap object within the TM. It's using the using the task manager memory. And you see it works well, but as the state size grows larger than fit in the memory, it's going to be a problem and cause the system to be unstable. So to solve this problem, we are, so to solve this problem, the embedded local DB is introduced to make use of the local disk. Typically, those DBs are co-located with compute to achieve faster fast access. And to guarantee the data consistency, a global checkpointing mechanism, as mentioned before, was designed. Basically, what it does is it's dumping the working state files from the local disk, from the local DB, periodically to the DFS to make a snapshot of the make a global snapshot of those state, and then upon failure or recovery, it will read back those files and then rebuild the state and resume the processing. Okay, so then, if state size is growing larger than fit into local disk, then it's going to be a problem again, right? So that's what we introduced the disaggregated state, and this is a cloud-native solution in Flink 2.0. Let's see what it is. So the disaggregated state, the architecture in the core is the forced disaggregated state backend. So it gracefully handles large states using a truly cloud-native design and employs DFS as the primary state storage. So what it is capable of? So it enables independent computation and storage scalability. Of course, right? Because now since we use the DFS as the primary storage, basically you have unlimited state storage and not limited by the local disk size anymore. Then they can scale independently. And also having the working state reside on DFS directly and read and write to DFS directly enables the capability to physically share the files between working state directory and the checkpointed directory. That basically says during the time when you're doing the checkpoint, you do not have to dumping all the files to the remote storage because it's already there and all the physical files could be shared. And this enables a lightweight and fast checkpointing mechanism, which we complain a lot in a local embedded solution where as the state size grows large, you periodically dumping would cause the system unstable and takes prolonged checkpointing time. And for the same reason, the instant recovery and the rescaling is also possible in this case because you read and write from the DFS directly, and as long as the state DB is rebuilt from the remote files, you do not need to download the files again to the local disk. So your application could start processing. So you can have instant recovery and rescaling and avoid a huge amount of data being transferred during this process. So the reason is the same for the lightweight and fast checkpointing. And also, we introduced the remote compaction service to further separate the DB operations out from the normal data processing. So now your data processing is uninterrupted and totally be separated from the DB operation. So there are two separations here. One is the separation of the DB operations. The other is the separation of the DB accesses from the computation. So all this together, we generate a uniform and smooth resource utilization. So this is the overview of Flink 2.0 architecture, and we mainly did the augmentation of the architecture in two layers. One is the runtime layer to introduce the async execution model, which decoupled the state access from record processing. At the same time, we preserve all the Flink 1.x core semantic guarantees like data correctness, checkpointing, consistency, low watermark, semantics, and etc. And to make sure that the execution model is fully compatible with Flink 1.x. The second part is what we do is in the storage layer, which, as we showed here, is the forced disaggregated state. So it decouples the resource-intensive state operations from the normal data processing, as mentioned before, and it allows zero copy between checkpointing and a working directory, so that when you're doing the checkpointing or recovery or rescaling, avoid a huge amount of data copy. That's actually save a lot of money and also time. And well, okay. And the last one is we have effective cache mechanism to boost performance. Well, since cache is very important in the cloud remote setup. And let's go in a bit detail into the async execution model. So async execution model is introduced mainly because the remote access is much slower than the local read. It's 100 times slower. And these are numbers, and it's all in the paper that I'm probably not going to in detail. But to solve this problem, we have to get rid of to pull out the remote reads from the normal processing and pull it so that it won't block the normal processing. In this way, we actually redefine the life cycle of the input record processing. Now it was divided into 3 parts. One is a non-state transformation. That's basically stateless transformation, right? And the second part is state access. And then the third part is post-state callbacks. That's what you do after you retrieve the data. So the first and the third parts are CPU intensive, so they are still executed in the task thread, while the second part now are pulled and executed in a different threading pool. Well, you know, the execution model is changed, and how we can guarantee all the core semantics. We introduced the asynchronous execution controller, AEC, as the brand for the async execution. So it does intra-task scheduling for async processing to preserve per key FIFO order. This is the foundation for the data correctness for stream processing. The second part is we introduce async draining mechanism to guarantee exact once processing. This is to guarantee data consistency. And the third part is we introduce the epoch mechanism to enforce low watermark event time order. Okay. And forced disaggregated state is used in conjunction with the execution model. And you see, as I think a lot of things has already been mentioned. So we now have the active working state stored on DFS directly. So data could be accessed through DFS directly without relying on the local disk. And we provide a unified file system that's providing the UFS linking to implement the zero copy between files of checkpoint directory and the working directory. And this capability enables light and fast checkpointing and instant recovery and rescaling. And also, as I mentioned, the remote compaction service was introduced to decouple the normal data processing from the heavy DB operations like compaction. Okay. And the last one is the tiered memory and the file cache that to boost the performance. And one thing that I want to highlight here is the entire enabling of this complicated mechanism is very simple. That's simply that you just set your state backend.type to forced. And since the execution model and since the execution model and the state backend are fully compatible, so your 1.x query could directly run in this, especially in the SQL queries. Okay, so here are some results. These are the probably 4 dimensions that's mostly be cared by users, and these are results generated from the real-time use case that I just we just talked about at the beginning of this talk. So there are two parts to see whether we claimed has been implemented. So the first part is the total cost drops half. Like, I don't have time to go in detail, but that's the first part. The second is the rescaling is also very fast. The rescaling and the recovery is also very fast. In all these three cases, restore, scale, rescaling, and scale out, the time is within 10 to 20 seconds, and both on HDFS and OSS. And then now for the checkpoint, wow, that's amazing, because I marked the threshold, the time spent in Flink 2.0 in yellow, in all these four cases. So you can see the checkpoint time could finish consistently in Flink 2.0 within 3 to 4 seconds. And comparing to the Flink 1 versions, they are actually exhibit long tail behavior because of the long tail problem for the DFS. And at last, it exhibited the uniform and smooth resource utilization. So these results are and also are reported in the VLDB paper as well, and with the very detailed setup, and with also a modernized example be provided. So if you're interested, you probably could play it yourself after the camera ready version is ready. Okay, so we claim that we achieve all these this good stuff, and people complain. What about the performance? And have you trade off these good things with something? Okay, now let's see the performance. That's also very important. We are using Nextmark queries. And Nextmark queries are standard stream queries, streaming benchmark, a set of standard stream benchmarks for testing the performance of streaming engines. So let's see what's its behavior in Flink 2.0. So overall, Flink 2.0 with DFS achieves, with DFS as the as the primary state store, achieves comparable performance with Flink 1.x with local SSDs. And to be, its color is different. And jump into a bit more detail. So using Flink 2.0, leverage the forced DB that we provide. It actually offers a direct alternative to Flink 1.x using RocksDB, which leads to a seamless upgrade path. And also, it is performance neutral for low I/O, which says this is actually do not brought up extra overhead, which is good. And for the heavy I/O, even with a modest 1 gigabyte local disk cache, Flink 2.0 supports the performance of Flink 1.20. So if you want to understand why all these achievements is being accomplished, then probably go to read the detail in the VLDB paper this year. And this is the team photo, and I'm very grateful to work with all these people with big dreams, and also thank the whole community for their support and the contributors. Okay, let's go into something new that we haven't talked about before. Generic incremental compute. And since we already solved all the problems for large states, not stable, slow checkpoints, slow recovery, then what's the next? So I want to make the real-time processing affordable by everyone. That's the mission. Through the generic incremental compute. And the generic be bigger than other things. Why? Because we talk about the incremental compute long time. And this is not something new word. And I heard this concept about 10 years ago. And this concept was brought up again these years, and their benefits were raised up. And people sometimes ask me, oh, how Flink? What's the role in Flink in this incremental compute? Well, generally, if people ask this question, I would think about the problem in these 3 dimensions: what, why, and how. And why is very clear, right? Because it's near real time, and most importantly, it's reduced costs, and it provides unified stream and batch processing. But what and how? So incremental compute, if we just sort to apply for a limited scenarios and simple scenarios, that's easy. But if we're talking about generic full coverage of data processing, it's difficult. That's why all these years this concept was there, but it's not being implemented. So let's see what is incremental compute. Well, I understand something is best. The best way is to compare with something that we already know. Now let's compare the incremental compute with the full compute, or namely batch compute. So for a full compute, the input is a complete input data set, and we process on top of the complete data set all at once, and generate a full output and overwrite the result table. While for incremental compute, we process on a delta input data set, and we execute the delta input set based on the history data, and especially if you need to correlate with the historical data. And the output has to be, then the output is a delta output that you have to merge to the result table. So you see those 2 execution paradigms, they are very different. And now let's compare it to stream compute. And stream compute, the input is still also delta, but each time it's just 1 record. And the execution is also per record, also need to based on the historical data. And as for the output, it produces a delta output and merge to the result table with delta equal to 1. Well, everyone here, this should be very easy to understand, right? Because you are expert on streaming, batch processing. And this seems very completely the same for stream compute, but with delta equal to 1. Then let's step back and think about it again. So for the incremental compute, these are the 3 key problems you need to resolve. You need to capture the data change. You need to process the captured change based on its memory. And then you output change log and merge to result table. And these are already being resolved in the streaming processing model. And the only difference is that we need to handle the batched input in a pipelined way. Okay, so I don't have too much time, but I want to highlight something that how we going to solve this problem. And for stateless computation, again, it is simple because 1-by-1 processing, it does not have too much differences in the cost point of view from the batched processing. However, if we are talking about more complicated processing related to the stateful computation, there is much more difference here because per record processing actually wastes a lot of that needs actually a lot of intermediate computation and waste a lot of processing cycles as they are probably not needed. So what we do is we extend the forced disaggregated state to forced disaggregated incremental state to make it capable of processing record at a time to a batched record processing, and making it have 3 capabilities. First, we'll have the compaction service to incorporate computation. So we can do push-down computation in the separate compaction service. The second one is the async bulk execution could provide a way to do the flexible state composition. So the state composition. So the query coverage could be much richer now. And the third one is we are providing the MVCC mechanism to enable pipeline incremental compute, so that when you're doing the computation, at the same time you can still accumulate the input batch. Okay, here is the comparison about the incremental compute between stream mode and batch mode. So because of time, I probably won't go into detail, but the highly part is their basically model is different. In the streaming mode, it's pipelined. In the batch mode, it's periodically scheduled. And because of in the pipeline mode, because of the the latency is easy to track and adjust, so the processing time could be guaranteed. While on the other hand, scheduling time doesn't necessarily mean or have any guarantees for the processing time. And from the flexibility and the query support point of view, streaming mode can support much more complicated operators and delivers a full coverage, versus in the batch mode, it's only able to cover very simple scenarios, and to do the full coverage is very difficult. And also from the cost point of view, they are both very low. And this work is currently internally in progress in Alibaba, and we plan to contribute to the Flink community in the following releases. And I think that's another game changer for Flink stream processing, and make the real-time processing really affordable by everyone. And that's our goal and dream. Okay, so here are the takeaways. I'm talking about what Flink's data is capable of, and how to solve the large state problems, and what's next. And do not have time to read them again, but hopefully after this talk, you could get answers and a meaningful agreement with me on the past, today, and the future. Okay, thanks everyone.